Okay, this module is going to overview the three basic passive elements that we're going to discuss in this class. So in this context, a passive element is an element that cannot supply energy for infinite amount of time. Generally, we think of passive elements as absorbing or storing energy. So the ones that can store energy, they can release that energy, which means that it would be a negative power, but for a very finite amount of time. Okay, so a passive element cannot supply energy for infinite amount of time. So we will deal with three primary passives: resistors, capacitors, and inductors. Okay, starting with the resistor. So resistance is defined as the capacity of a material to impede current. We measure this in units of ohms, which uses the Greek symbol omega. So a resistor is merely a circuit element that models this behavior, this resistance. So what we're going to do is replace our black box circuit element that we define with passive sign convention with this symbol shown here, where it's a little kind of staggered triangles, and then we usually put a value next to it, and that would be defined as the resistance. Note that we still use passive sign convention to define the polarity of the voltage and the direction of the current. So resistors effectively just convert electrical energy into heat, and that's going to be the absorption of that power. So resistivity is the fundamental property of a material used to make a resistor. It describes how strong a material opposes current. So if we consider a rod of material, shown here, we can define the length of that, the cross-sectional area of the rod, and then the material property. And that's what we call resistivity, and use the variable rho for that. So for this rod, the resistance of the rod is going to be directly proportional to the length. So the longer the rod it is, the harder it is to move charges through the rod. It's got to go further distance. It's going to be inversely proportional to the cross-sectional area. So a larger area more readily allows charge to flow through it. A smaller area restricts the charge. And then the constant of proportionality is what we call resistivity. So looking at the units, since resistance, let's see, I keep pushing the wrong one. Since resistance is in units of ohms, we have length in meters and area in meters per squared. We can see that resistivity is in ohm meters. Okay, it's a material property. It's if you come up with a cube of material, you would find the radial length of that. The material has an ohm meters, and then you would multiply by the radial length as well as the cross-sectional area of the material used to get out the total ohmage, or the resistance of the material block. So since it depends on this material property, it varies according to material. So metals, which are good conductors, have very low resistivity. Glass, which are good insulators, thermally as well as electrically, have high resistivities. So if you want a large resistor, you could use less material. If you use a glass material to create that large resistance, than you would need of metal. You would need a lot of metal in order to get the equivalent resistance. When we have zero resistance, that would be ideal. That's what we refer to as a superconductor, an ideal conductor, because we don't have any attenuation with the movement of charge. So again, when we draw wires in class, we're assuming that those have zero resistance. So you can also quantify what's called the conductance of an element. And we usually do this when resistance is just very small, say less than an ohm, for example. Conductance is measured in units of Siemens, which is a capital S. Sometimes, like the old school way of describing this is the mho, ohm backwards, and you just draw the ohm upside down. Both of them mean the same thing, where conductance is just the inverse of the resistance. As I mentioned when I talked about the generic element that has two terminals and can be described by a voltage across the element and a current through the element, I mentioned that as we sub in these elements, we will also have a functional relationship between V and I that describes the specific features of that element. Ohm's law is that functional relationship for a resistor. and it states that voltage is directly proportional. The voltage across an element is directly proportional to the current through an element. In other words, V equals I times a constant of proportionality, which is what we call the resistance. So now we can draw the symbol of a resistor with the passive sign convention in its place. So note that in this case, V could be positive or negative, but since it's a passive element, we know that power is going to be positive. So if V is positive, I must also be positive. If V is negative, I must also be negative. And then we can rearrange the equation of Ohm's law to solve for resistance, and we see that 1 ohm is really equivalent to 1 volt per amp. Okay, so now let's arrange the resistor in a basic circuit, shown here on the top. We're just going to wire a resistor directly to a voltage source. And as I discussed in the last module, when we do this, voltage source V ties straight to the resistor. It shares the top terminal, and it shares the bottom terminal. Therefore, voltage V is also across the resistor. So then we can draw the current I based on passive sign convention as going into the positive terminal of the resistor. Because of that, we can then write the equation that P absorbed by that resistor just equals the voltage across the resistor times the current through it. Subbing in some values from Ohm's law, V equals IR times I gives us a power equation of I squared times R. We could have written that by subbing the equation in for I, that equals V over R, and seeing that power also equals V squared over R. Doesn't matter which one you use. VI, I squared R, V squared over R, they're all equivalent. When we look at it in this form, though, I squared R or V squared over R, we see right away that this confirms that power must be positive for this element, regardless of the sign of either the current or the voltage, because of the square term in each of these equations. So a resistor always absorbs or dissipates power, and it does so as thermal energy, heat, conversion of energy into heat. That's why our light bulbs get hot, or our toaster gets hot, or our laptop gets hot, for example.